Good day to everyone. In this video, we are going to show the procedure for solving the heat equation. So the heat equation is actually a partial differential equation satisfying a set of conditions. So in this case, the I'm showing my whiteboard where you have in the first equation a partial differential equation. And this partial differential equation will have to satisfy three conditions, namely the following. We have u of 0t equal to 0, u of 1t equal to 0, and u of x0 is equal to x minus x squared whenever x is an element of the closed interval 0, 1. So let's go right ahead and um, start the solution. The basic idea in solving this partial differential equation is to assume that our function will come in the form of a product of two functions, namely capital X of x times capital T of t. And if we try to substitute this into our partial differential equation, what we will get is the following. We will have capital X of x times capital T prime of t will be equal to k times capital X double prime of x times capital T of t. Now, to simplify our calculation a bit, we will assume for the time being that k is equal to 1 over alpha squared, which is basically a positive number, and alpha, of course, will not be equal to 0. Okay, so with that said, from the last equation, we will get, after rearranging some of the terms in the equation, we will have k times capital X double prime of x all over capital X of x is equal to capital T prime of t all over capital T of t. Okay, and so with that, we can also write, because of this assumption, we have 1 over alpha squared capital X double prime of x all over capital X of x will be equal to capital T prime of t all over capital T of t. And as a consequence of this, okay, you will notice that the left side of this equation is solely in terms of small x, whereas the right side is an expression solely in terms of small t. And those expressions must be equal for all possible values of small x and t. So this will imply then that these two expressions will have to be equal to a certain constant. Now, in the end, we want a solution u of xt that will exhibit some kind of oscillatory solution. So an oscillatory solution will result from making this common value for the constant be a negative number. So what I will do is I will let this common value to be equal to minus lambda squared, where I know that lambda will be a positive number, and so minus lambda squared will be a negative number. So this will imply then that I will have 1 over alpha squared times capital X double prime of x all over capital X of x is equal to minus lambda squared, and um, capital T prime of t all over capital T of t is equal to minus lambda squared. Incidentally, each one of these equations will give rise to, first of all, the second order ordinary differential equation, capital X double prime of x plus alpha squared lambda squared times capital X of x equal to 0. And we have the first order ordinary differential equation, capital T prime of t plus lambda squared times capital T of t equal to 0. Now, I will assume that the listener is already familiar to the kind of solutions that we will get for each of these differential equations. So the first one will give us a solution which is capital X of x equal to a cosine alpha times lambda times x plus b times sine of alpha times lambda times x. Whereas for the first order differential equation involving capital T of t, we will get the function capital C times e to the negative lambda squared t. So that we will now have our initial expression for our solution u of xt, which is c times e to the negative lambda squared t times a cosine of alpha times lambda x plus b times sine of alpha times lambda x. And what I can do here is I can distribute the factor c into the bracketed expression and then rewrite this as follows. So e to the negative lambda squared t times p times cosine of alpha times lambda times x plus q times sine of alpha times lambda times x, where I know that p is equal to ac and q is equal to bc. All right. And so now we are ready to apply the different conditions that are given in the problem. And first of all, we have, let's see, so u of 0t, which is the first condition. This would imply that upon substitution of the value x equals 0 into our first version of the solution u of xt, we will have e to the negative lambda squared t times the quantity p plus q times sine of 0, and this must be equal to 0. This is equivalent to p times e to the negative lambda squared t equal to 0, from which, because we know that e to the negative lambda squared t is always positive for all values of t, then this will imply that p is equal to 0. So we can edit our function u of xt, and upon substitution of p equals 0 into u of xt, we get e to the negative lambda squared t, and then there's a q here, so let me just insert the q here, and then we multiply that with sine of alpha times lambda x. And so now we are ready to continue with the solution by using the next condition for the heat equation, which is U of uh, 1T equal to 0. So we are now going to use this equation, okay, and substitute x equals 1 into this expression so that we will get the following. So we have q times e to the negative lambda squared t sine of alpha lambda x must be equal to 0. Now, what are the things that we can tell from this equation? Well, for one, we can say that q cannot be equal to 0 uh, because, firstly, if q is equal to 0, then that would make our function u of xt solely equal to 0. And so that will actually be a solution which is not interesting. And secondly, this will actually run contradictory to the third condition, which says that u of x0 will be equal to x minus x squared over the closed interval 0, 1. And so it's imperative that q here is not equal to 0. Incidentally, e to the negative lambda squared t is always positive, and so there is only uh, one conclusion here, which says sine of alpha lambda x must be equal to 0. Oh, by the way, let me do a little bit of correction here because we have already uh, we're supposed to have substituted x equals 1, so we should only have sine of alpha times lambda. Okay, so let's try to correct this. All right. Now, so sine of alpha times lambda must be equal to 0, which implies then that alpha times lambda must be a positive integral multiple of pi. So that should be equal to n pi, where n is equal to 1, 2, 3, etc., ad infinitum. And furthermore, lambda will be equal to n pi over alpha, where again n uh, ranges over the positive integral values. And so we can once again edit our function. So you will notice that lambda is actually a function of n being equal to n pi over alpha. Okay. And so because of that, we can also index the function u of xt in terms of n. In particular, we can have u sub n xt equal to qn e to the negative. We have n squared, pi squared, all over alpha squared, t, and then we have a sine of alpha times lambda. Lambda is equal to n pi over alpha, so n pi over alpha, and then there's an x here. And this will be simply be equal to qn times e to the negative. Now recall that I have let k be equal to 1 over alpha squared. So here I can say that the exponential term is equal to e to the negative k times n squared times pi squared t times sine of n pi x. And so having known now one particular solution of the PDE in terms of n, we can now say that the general solution is u of xt being equal to an infinite sum of these expressions. All right. So we have uh, this function u of xt, and all we have to do now is to be able to determine what exactly is qn. Note that this is going to be the coefficient of the solution for our infinite sum, which will represent u of xt. So now we can use the last condition in our heat equation. So we are also given that u of x0. So now u of x0 must be equal to x minus x squared on the closed interval 0, 1. So this will imply by direct substitution that u of x0, which is equal to this infinite sum, must be equal to the infinite sum of q sub n times sine of n pi x. All right, so this is where we continue our solution, and furthermore, we have to let this be equal to x minus x squared on 0, 1. Okay. And from here, we try to apply one very important fact about representing functions in terms of half-range Fourier sine series. So let's write that information down. So recall, if f of x is equal to the infinite sum of bn times sine of n pi x over L, then the coefficients bn can actually be computed using the formula 2 over L times the integral from 0 to L of f of x times sine of n pi x. Okay, let's try to write this more neatly. So this is sine of n pi x over L dx. In our particular example, our capital L will be equal to 1 because our fundamental interval is the closed interval 0, 1, which will have a length of 1. So again, capital L is equal to 1. So this implies then that if we are going to compare the information that we just wrote with this equation, then what we get is that q sub n will be equal to 2 over 1 times the integral from 0 to 1 of x minus x squared times sine of n pi x dx. Now, I'm not going to go over the actual integration by parts for the evaluation of this integral. I will go right away and give the neat expression for this integral. So it is going to be equal to 2 over pi cubed times 1 minus negative 1 power n all over n cubed, which is also equal to 4 over pi cubed times 1 minus 1 power n over n cubed. And again, I invite the listener to just verify later on that indeed this is the proper representation for um, the coefficient q sub n. And so because of this, we can now complete our expression for the solution u of xt. And in fact, it's going to be equal to the infinite sum of q sub n, which is equal to this. So 4 over pi cubed times, so this is supposed to be a cubed, 1 minus negative 1 power n all over n cubed times e to the negative k n squared pi squared t times sine of n pi x. Or finally, we can bring out the constants from our infinite summation so that this will become 4 over pi cubed times the infinite sum of 1 minus negative 1 power n over n cubed times e to the negative k n squared pi squared t times sine of n pi x. And so this is our solution for the heat equation satisfying the three conditions that are given to us. So thank you for listening. Thank you very much, and I'll see you again in the next video.